मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी।
Well, this is 8th lecture in the series of mechanics of metal forming. We would cover representation of a tensor. Usually whatever chapters now we are going to discuss, particularly we are going towards the analytical part of metal forming. So it is very necessary to discuss the tensor, because everywhere the equations, metal forming equations, plasticity equations, whatever it comes, that is represented in the form of tensor, because the tensor form reduces the size of the equations and it is a very compact representation. So in this particular lecture we would discuss the representation of tensor, particularly for mechanics part of when we represent the stresses, strain and the related equations. So the tensor and related issues, and we would be solving some of the problem to understand how the tensor representations could be solved and it means in different equations of the form. So let us see, we usually come across the modeling of metal forming processes, basically the physical quantities in the form of scalars, vectors and tensors, very often we come across. So what is tensor? Let us see what is tensor. So in fact a tensor, it means the order of 2 unless it is stated. If it is nothing said, that means the tensor order is 2. Otherwise a 3-dimensional space, if you take a 3-dimensional space, so a vector has 3 components and therefore a tensor has 9 components if we look into. So as far as the indexing notation has to be followed for representing especially 3-dimensional tensor, which is of use for metal forming, the components corresponding to the index as well as whatever expressions are being formed involving scalars, vectors and tensors, let us see. Let us see this index notation. It works on especially your coordinate axis x, y, z, and let this coordinate axis be represented as 1, 2, 3. Therefore for an example, if we represent 1, 2, 3 in the form of a particular velocity vector vx, vy, vz, so we can simply write as the vi. So in the tensorial representation we can write vx, vy, vz as vi, right. So the vi means 3 directions, I represents 1, 2, 3, 1, 2, 3. So vi means it's a tensor, so having 3 components v1, v2 and v3. So 1, 2, 3 represents 3-dimensional space, and therefore if we take in 2-dimensional space, it can take value I as 1 and 2 only. Similarly the notation, suppose there is a stress ij, if we write the stress ij as notation with the indices as I and j, so how many components can be, because now the I and j, I ranges from 1 to 3 and j also ranges from 1 to 3. Therefore, how many? 3 multiplied by 3, that is now 9 component of the stress is possible, and therefore the stress tensor will have, that is sigma ij, it will represent 9 component, like sigma 1 2, sigma 2 3, sigma 3 1, then sigma 1 1, sigma 2 2, sigma 3 3, and sigma 1 3, then sigma 3 2, then sigma 2 1. So these becomes almost 9 components. In fact, if we see this notation, it was it came from the Einstein summation convention. Einstein used some summation convention, and therefore the similar convention is implied for writing the sum of various terms in a very condensed or short form. And it has been found that this convention, if indexing is used, so it can occur twice in a term. Then the term represents the sum of all the terms involving all possible values of the index. For an example, if we take, say, a situation where ai bi, that is that means I, if it is ranges from 1 to 3, so if I write a convention as ai bi, that means it mean a1 b1 plus a2 b2 plus a3 b3 in 3-dimensional space. And likewise, for an example, and so therefore one can see here that whatever convention we are going to use, for an example, let us take the term aij. If we take another convention as aij bj, so we have there is a index, there is a dummy index, and there is a free index. There, if you see, if there is a dummy index and there is a free index, so if you see, the dummy index is repeated, whereas the non-repeated index, which is called as free index. Thus, if you write as aij bj, so a is free index, the I is free index and j would be taken as dummy index. So any symbol can be used for any index, dummy index, and therefore the index, the expression that it is there, this particular expression, if we take here, that is aij bj, it can also be written as like aij bk. So k is another index which can be changed. When there is two dummy indices, like that mean will cover the sum over both, that is a 3-dimensional, it will become 3-dimensional. It will contain in therefore how many terms? For an example, if we take a term like aij bij, if we take this term as aij bij, that means how many because I varies from 1 to 3 and j varies from 1 to 3. Therefore, if you take the component and then summation, so there are 9 components are added. So what would be your if you expand aij bij, that will it will be expanded as a11 b11 plus a12 b12 plus a13 b13 plus a21 b21 plus a22 b22 plus a23 a b23 plus a31 b31 plus a32 b32 plus a33 and b33. So this is the summation of 9 components, and it is simply represented in a very simple form aij bij. So the index that which is repeated more than twice, it is an invalid expression if it is repeated more than twice. So an expression or equation containing no free index represents a scalar expression or scalar quantities. Therefore, similarly, an expression or equations containing one free index denote a vector representation or quantities, and an expression or quantities containing two free indices represents a tensor. Therefore, expression either in the form of expression or equations. So say let us take an example here, like the term sigma ii. Let us take the term sigma ii, which will, because it is now repeated, so sigma ii it is repeated as a scalar. Therefore, the term aij bj, if it is written like aij bj, which is containing free radical as free indices as I, which represents vector, while the term if we say as say r ij and sjk, say it is rij and sjk, so this contains the free indices as I and k represents the tensor. Similarly, equation if we write equation ai bi is equal to c, if we write this particular equation ai bi is equal to c, this represents a scalar equation. Okay, and let us see these equations. So if this equation, that is the stress ij, that is the and nj is equal to ti. So the free radical is I and dummy radical is z. Okay, so the free index is I and dummy index is j. Now if you see here, if we see here as a p ij, which is equal to q ij and r kj, if this is the equation, that is p ij is equal to q ij r kj. So the free indices is I and j, free is I and j and dummy is k. So these two equations, this particular equation denote a vector and tensor equations respectively. So in an equation where all the terms should have the same number for free indices, further the notations that we follow for free indices should have the same in all the terms, otherwise it will be it will not represent a correct form. Thus, if we take this particular equation where if let us take as I capital I is equal to AJ. So, look at this one, I capital II is equal to AJ. So, there is no free index here on the left side, right? And let us see this one, if Pij is Q Pij is equal to QKL, if it is this equation. So, you have two free indices have different notations on the two sides. Here it is Ij, here KL. So, these are all invalid expressions, right, because it will not represent. So, with this particular fundamental where you can represent the summation in this form of notations, let us take some example. Let us take problem number 1, where you have the first problem where the expression is Ti is equal to sigma ij nj. So, let us expand this problem number 1. So, how would you start? This is what, a vector or tensor or scalar, because it is ij j and on the left side it is Ti. So, this represents a vector, it can't be a tensor. So, this represents a vector equation, as there is only one free index which is I on each side of the equation, and whereas the dummy index which is j on the left side indicates that it is a sum of these terms. Expanding this sum, one can find it out like here, that if we expand it, so that is Ti would be sigma I1 N1 plus sigma I2 N2 plus sigma I3 N3. Is this okay? Now, since I is a free index and takes the value 1, 2 and 3, up to it can take any value 1, 2, 3. So, this vector equation actually represents 3 set of scalar equations. Say first I remains same. So, sigma I1 N1 plus sigma I2 N2 plus sigma I3 N3. Now, if because the free radical which is I, if both side it is I, so I can now change I from 1 to 3. So, that will 3 such equations. So, that means T1, first equation would be T1 is equal to sigma 11 N1 plus sigma 12 N2 plus sigma 13 N3. Similarly, the traction 2, that is T2, would be sigma 21 N1 plus sigma 22 N2 plus sigma 23 N3, and then T3 would be sigma 31 N1 plus sigma 32 N2 plus sigma 33 N3. So, this is how a very simple equation Ti is equal to sigma Ij Nj is very short form, but it represents 3 such equations. Let us take another problem and let us write the indices notation for the following expression. let us reverse the things. Here it is sigma n, it is given as sigma n is equal to sigma 11 n1 is square plus sigma 33 n3 is square plus in bracket sigma 12 plus sigma 21 and then n1 n2 plus in bracket sigma 23 plus sigma 32 n2 n3 plus in bracket sigma 31 plus sigma 13 bracket close n1 n3 and n1. Let us write the index notation for this particular equation. So we are be writing the reverse, the first problem we did initially. So what we should now note it here. There are how many terms? 1 2 3 4 5 6 7 8 9. So there are 9 terms here. Therefore the indices notation must involve 2 dummy indices and one as free index. So in order to write the above equation in terms of the dummy indices, we rearrange the right side of this particular equation like here. Let us open the bracket and rearrange. So we can write down as sigma n is equal to sigma 11 n1 n2 plus sigma 12 n1 n2 plus sigma 13 n1 n3 plus sigma 21 sigma n2 n3 plus sigma 22 n2 n3 plus sigma 23 n2 n3 plus sigma 31 n2 n1 plus sigma 32 n3 n2 plus sigma 33 n3 n2. So now you can note in this equation number 10 that each bracket there is a sum over the second index of sigma and the index of the second n. You see here in the first term 1 1 then 1 1 1 2 1 2. So you can see the repetition. So this sum can be expressed using a dummy index which is denoted by j. If we denote it by j, and then the same expression which is very long expression can be expressed as sigma n is equal to sigma 1 j sigma n1 nj plus sigma 2 j sigma n2 nj plus sigma 3 j n3 nj. Now there is a sum over the first index of sigma and the index of the first n, whatever it is. So one can express this particular sum into another dummy index taking as I. So the finally this equation can be written at in which form? Sigma n is equal to sigma ij ni nj. So now you see such a long equation is represented in only 3-4 terms. So that means it is ni sigma n is equal to sigma ij ni nj, and you can see here the symbols corresponding to the dummy indices can be which is other than the I and j. So this is, it represents a tensor there, it's a vector form, but it is a Usually two symbols are used to simplify the short expressions in the index notation form, and we use very often chronicle delta. We call it as a chronicle delta, which is which can be permutated. So permutation symbol it can be used. So the chronicle delta is defined as here, it is a delta ij is equal to 1. We write delta ij, which is a chronicle delta. So delta ij is equal to 1 if I and j is equal to same. If it is I is equal to j, we take delta ij 1, and if it is 0, we take when the I and j are not equal, unequal. So this permutation symbol we can define it by other form, like here. For an example, if we define this here like ijk, so this is for the I and j when it is, but when it is a three dimensional chronicle delta, if we define, so say strain ijk is equal to 0 if two or more indices are equal. If two or more indices are equal, we take it as 0. We take it as plus 1 if I, j, k are even permutations of 1, 2, 3. So we would be taking this strain rather I, j, k is equal to plus 1 if I, j, k are even permutations of 1, 2, 3, and it will be taken as minus 1 if I, j, k are odd permutations of 1, 2, 3, right. So the symbol chronicle delta and this strain the following identities. So this identity basically, where we can write it as a1 delta ij. If you write it like this, ai delta ij, so it can be, it will represent aj. For an example, this, and let us take this identity, aj capital Aij delta jk, which is equal to capital J A jk delta Ij delta jk, and it will be taken as delta jk. So and then suppose this case is here, if you write strain ijk, then strain pqr, if both are together. So in this format, in the chronicle format, if you write, so what would be the chronicle that is IP, chronicle IP in bracket chronicle delta IQ chronicle delta KR minus chronicle delta ER chronicle delta K KJ plus in bracket chronicle JR chronicle KP minus chronicle IP and chronicle KR, and plus chronicle IR, then in bracket chronicle JP chronicle KQ minus chronicle JP chronicle KP, right. So this chronicle symbol chronicle delta, when it is replaced, it will change according to the values, and as the indices comes into, for an example, if it is I and j only, so it is equal to 1 when I and j is equal, and it becomes 0 in case I and j are equal, non-equal. And similarly, when ijk, the permutations are defined in this format ijk, that is the strain, it becomes 0, it becomes +1, and it becomes -1 depending on the even and odd combinations. Let us take an example, the problem here, third problem, and let us expand these expressions. So the expression is number 1, which is C is equal to A B J and chronicle delta Ij. So the C is AI Bj chronicle delta Ij, and second expression is D is equal to strain Ijk and then Aj B. Let's expand it in the similar format which is the chronicle we have. So if you look into, this is a scalar equation. First thing is, because both the side it is not equal, indices are not equal, it is a scalar quantities involving two dummy indices I and j, and thus it involves a sum of 9 terms. So if we take the first case, if we expand the first sum, so the sum over I, we get the following terms on the left side of the equation. So then it becomes C is equal to A1 Bj delta Ij plus A2 Bj delta 2j plus A3 Bj delta 3j. While expanding the sum over j, now this is the first expansion over I, and then once you expand over j, so each of the 3 terms we would follow the expression, earlier equation of the where the chronicle delta according to when equal and non-equal, and accordingly it will be substituted 0 or 1. So if you substitute over the j, so this can be written as C is equal to A1 B1 plus A2 B2 plus A3 B3, because other terms become 0 because of where it is A and B, I and j are equal, the notation indices notation the values are equal, then it will become 0, and therefore it becomes so simple. Now note this particular equation on the right side of the equation, that equation number 20, where the Aj Ai Bi, thus we get the what identity we would get, Ai Bj delta Ij, Ai Bj delta Ij, so that becomes Ai Bi simply. So this expression becomes a simple Ai Bi. So this is what it simplifies. And let us take the second part, where the strain Ijk, the second expression, where it involves 3 dummy indices. So if there are 3 dummy indices, means it is a sum of 27 terms, 3 multiplied by 3 multiplied by 3, so 27 terms. However, the value of the permutation symbol in the form of strain is 0 when 2 of its indices are equal. Therefore only 27 minus 6, 2 multiplied by 3 6, that means 21 terms would be 0, and therefore the expression with the second part of the expression will be with the remaining 6 non 0 term would be D is equal to strain 1 2 3 and capital I1 A2 B3 plus strain 1 3 2 I1 A3 B2 plus strain 2 3 1 I2 A3 B1 plus strain 213 plus I2 A1 B3 plus strain 312 I3 A1 B1 plus strain 321 I vector I3 A2 B1. So this particular, if you go back to the equation number 14, where the situation and if you substitute the values of the permutation symbol according to the definition of the chronicle delta, so this can be written as simply, because the other term would be 0, so D is equal to I1 and A2 B3 minus A3 B2 plus I2 A3 B1 minus A1 B3 plus I3 A1 B2 minus A2 B1. So one can note here on the right side the cross product of the vector A and B, and therefore the cross product, so if we take the cross product A cross B, so that would be epsilon. This is also called as epsilon ijk, and vector I aj bk. So that's a simplified one. So one can note down the meaning of these indices. Let us take another problem, and let us find out the determinant of a matrix A, which is given by this. So which is given as determinant A is given as 1 by 6, and the chronicle delta, which is LNM, and the epsilon XYZ, and then A LX, A MY, and A NZ. So suppose this is a matrix, it represents a matrix. So in that case, can we represent it? So the constants on the component of A, if you look into the matrix A, where we have that is non-diagonal components, if you look, so these, it will satisfy the notation like Aij is equal to Aj I, it will, because they are non-diagonal terms. Secondly, the sum of the diagonal component would be 0, because and therefore the components are the capital A, AK would be 0, and using the above constant, let us show the expression for the determinant of the equation number 25. It will reduce to determinant A would be equal to 1 by 3 A JM, A MN, and A NL. So it will be simply here. So you see, which was previously shown here in equation number 16, the determinant one can be expressed in the term of delta. So one can express, so determinant A would be equal to 1 by 6, and chronicle IX LX, and then in bracket it is delta MY delta NX NZ minus delta M NY, and plus similarly the delta LY in bracket delta MZ delta NX minus delta NX delta NZ plus delta, and so on. So one can see here that these these expressions can be modified using the identity of the previous equation number 15, which was will have only 6 terms. So determinant A can be represented as sixth term like 1 by 6 in bracket, that would be a L1 a mn a nn minus a L1 a mn a nm plus a ln a nm minus, and likewise here. So if you further modify the second, fourth and sixth term which arises because of the symmetry of the equation, previous equation 26, so one can further write it is as the determinant a 1 by 6 a and this particular equation which is here. So in the slide it is equation 31, and then we can use constant on the diagonal term which was in the equation number 27 there to simplify the above equations. One should note the index, particularly k in the equation 27, which is a dummy index, and thus it can be replaced by any two index, and therefore the first, second, fourth and sixth term becomes 0. Automatically it becomes 0 according to the chronicle delta definition, which is, and therefore the equation number 31, this particular equation, it will be simply written as determinant a is equal to 1 by 6 and a ln plus a ml a nm plus a lm a mn and a nl, and then further we can modify the first term using the symmetry component of a, and therefore it comes out 1 by 6 a nl a lm a mn plus a lm a mn a nl. So finally when you substitute all the other order first term other term, we can we find both the terms which is identical, and one can combine in two terms, and therefore we get the expression in this form. So determinant a is equal to 1 by 6, this two sets of a, this and that. Now it will become simply 1 by 3 a lm a mn a nl. So now you see it is so small, one can see the long expressions can be represented using the tensorial. Let us take another example where the equation an expression and let us express derivative of aij with respect to a pq. So if take the derivative in the index notation, so likewise one can follow it here, and one can see that the derivative of aij with respect to a pq is 1 only if both the indices p and q are exactly equal to I and j. If any one index is different, then the derivative is 0. And for an example, suppose I is equal to 2 and j is equal to 3, which is different, then if both p is 2 and q is 3, then the derivative of a23 with respect to a23 would be 1. And however, the derivative of a23 with respect to a pq for p is equal to 1 3 are with respect to that is a2q, for when q becomes 1 or 2 it is 0. Thus one can get a very simple derivative, that is the derivative aij with respect to, and it will be equal to simply chronicle delta ip chronicle delta jp j q. So that's the simple derivative. So one can see the partial derivative of a component with respect to xj is indicated by comma, which is followed by j. For an example, if we represent uij, u comma j, ui comma j means it is derivative deva ui deva with respect to deva xj. So this is the simplified notation, which in turn represents the 9 expression again, because both and I and j varies from 1 to 3. So now this equation, for equation number 35, it represents how many terms? Say it is a 9 component, because so let us take an example based on this. Let us expand the following expression, which is sigma ij comma j is equal to 0. This is an expression. So if you expand it, one has to see that on the right side it is 0. So it's a vector. So it's a vector equation, as there is one free index I only, and dummy index z represents a sum over the 3 terms. Further, the comma represents j index. So sigma ij comma j, so indicates a differentiation with respect to xj. So if you expand the sum over j, the above equation can be written in the form of deva sigma I1 with respect to deva x1 plus deva I2 with respect to deva x2 plus deva I3 with respect to deva x3, and it is equal to 0. Because I is a free index and it can take a value of 1, 2 and 3. So this equation can further be represented with 3 scalar quantities. Say if when I changes 1, 2, 3, so that means this particular equation number 37, if it is expanded full, it will form a 3 separate equation having 3 terms each in one equation. So now one can see here deva 1 1, deva 1 2, deva 1 3, and with respect to deva x1, x2 and x3 respectively sum over, and that is equal to 0. Similarly with respect to sigma 2 1, sigma 2 2, 2 3 and sigma 3 3. So this forms a matrix. So this can be represented in a matrix, and this is what this basics of tensor is used in metal forming when the expressions are large enough, long enough. So we can represent in very brief without changing the meaning of the expression. So this particular tensorial representation would be helpful. In the next lecture it is on the state of stresses, and then later is state of strain, and then the flow, yield and flow lectures. Everywhere it is to be followed, and later also when the other part of the stresses strain relationship comes. So this particular definition of the strain representation and how tensor representation and how it is going to be used to represent the equations in a very short form is very useful for the subsequent lectures. One has to practice in the here we took around 5-6 problems to illustrate the meaning of the tensor notations, and one has to further practice, because in case of partial differential equations, if we represent it in this manner, it becomes further very compact. So with this, once again to tell you that this particular lecture also has got some objective problems, and you can test yourself the expansion, and you judge your understanding. I would like to thank you all for keeping patience during the session, and please I will again request you not to forget. Please give your feedback through the site which is given on the web, so that we can take your suggestion for improving our recordings. Thank you very much. Thank you. 200 mm, which is extended to 250 mm, say. So determine the value of the yield strength of the material of the bar after extension, and also determine the work done during the elongation. That the work done equation we have already calculated earlier, so we would make use of those equations here. So how to proceed? So certainly the true longitudinal plastic strain can be calculated as epsilon L, and that is 0.223 one can calculate. Now using the already given equation in this problem, one can calculate the final, this if you substitute this true strain epsilon L in this equation, you can find out the stress, final stress, as 466.15 megapascal. Okay. So because in the problem the work is given, because the work done is already given here, so the work done can be found out this particular equation which was earlier explained. We calculated the work done, so one can find out the this equation, volume divided by this, where the value of A, B, C is known to us. The value of A, B, C and N is known to us. Say A is 300, which is given here from the equation which is already given in the for the brass workpiece. Then B is also given from the format of the equation, that is 1, and C is given as 15, and N is also given as 0.3. So if you substitute, one can find out the work done as 3539.255 Newton meter. So this is how one can calculate the work done. These kind of work done is later utilized for designing requirement of energy for particular deformation and all that. It's a small method how to calculate the work done, and similar way later one can calculate the work done, which can be directly linked with calculation of total energy, and based on that the motor can be selected. A proper motor is selected and for the particular machine. Let us take the last problem, which is seventh problem. Another problem where an aluminum test piece of 100 mm long and 20 mm wide and 2 mm thickness is elongated to 130 mm. So let us assume that there is an anisotropy in this material. So if the anisotropy ratio is given as small r, let it to be 2. So how can we? Let us determine the true strain in the length direction, width direction and thickness direction. So how to calculate? In this problem, the anisotropy ratio is given for the sheet metal of the aluminum workpiece. So as explained in this lecture in the beginning, the anisotropy ratio, which is the ratio of the two strain. So it is given in the problem that epsilon W and divided by epsilon T is equal to 2. So if you have the three strains as epsilon L, epsilon W and epsilon T along the three directions, and because the plastic deformation, because of the continuity equation, so the sum of the strains, these strains must be equal to 0, and from the given value of R, if you substitute, one can find out, and because of the condition that the thickness direction and length direction would be, one would be the tensile and another would be compressive. So and this should be equal, however. So these are equal, then it is value of 0.262, and therefore one can calculate the value of in the thickness direction as minus 0.0873. So these equations clearly shows, this exercise, this tutorial clearly shows that the value of strains, and this can further be extended if you use a equation which includes strain rate. So there are equations available just like the power law you have, so that includes strain rate. There are equations which includes in temperature also. So if you use these equations of strain rate, temperature, one can further calculate these tutorial exercises. The list of book has already been given, one can refer to those equations, and you can go again with these set of tutorials in using the effect of strain rate, temperature simultaneously, and you can calculate. So this guides a very insight into the basic forming which we would be using in subsequent lectures. So far we have not discussed the stresses and strain. Next time we would discuss what is the state of stress, what is state of strain, and then how these stress and strain is related in the form of equations that we would be discussing. I would like to thank you all for your patience, and please these exercises, based on these you can evaluate your understanding. As I told you last time also, on the website the questions are, objective questions are there, you can answer them, and you can judge your understanding. Thank you for your patience. And again I would like to remind you, please do not forget to give your feedback so that we can improve upon our deliveries of all kind. Thank you very much.